binary tree is just a tree where you can have a root node, or you can have a right node, or you have a left node, or you have all both all together, and like this also you have certain set of trees with having leaves. This is what a binary tree, right? Without a root also a tree with or without nodes, that is 0 or more than one node, is known as a binary tree, right? Okay. So when you have a binary tree, you people already know this is binary tree. We have studied already. We have studied this in our data structures, right? Okay, then from this binary tree, we used to construct binary search tree. Okay, what is this binary search tree? Can anyone tell me what is a binary search tree? Even we have studied this binary trees in the beginning of the module 1. Beginning of the session, we have just gone with trees. We have seen the definition of trees, right? Tell me meaning of binary search tree. I want answers from you. Anyone? So binary tree is where it is having at most 2 child nodes. We have already seen this. At least it is having 2 child nodes at most. That is, it can have 1 child or only 1 child or even 2 child. This is known as a binary tree. Then what is a binary search tree? A tree where root node will, it will have a root node and it will have a left subtree which is lesser than root, and it will have a root which will have a right subtree which is greater than root, right? This is known as a binary search tree. Okay, where the root will be there, and compared to root, left side root will be smaller than this and right side will be larger than that. That is known as a binary search tree. Okay, for example, I'll take one simple example of a tree. For example, I take 8, I will write 3 here, and look here, this is the root, and for that root left side this will be smaller, 3 smaller than this. I'll write one more thing, 1, and I'll write 5 here. Look here. So 3 is also now child, a parent. For that, 2 children are there, 5 and 1. 5 is smaller. Smaller should be left on the left side and larger should be on the right side. Now I'll write one more here. For example, look here, it should be larger than this. Right hand side always should be larger. Then from this I'll write 11 and here I'll write 9. Okay, like this we have to construct a binary search tree. A tree where root will be having and the left subtree will always be lesser than the root and right subtree will be greater than the root. This is known as binary search tree. Okay. This is just an example we are giving. Okay. So when certain set of elements are given, for example, I'll give you some 5, 10, 20, 30, 40. Okay, when certain set of examples like this, some set of elements are given, I need to search for an element in this. So what we do to do searching, we use linear search, and what is a very important search we did? Binary search. Okay, this is what we do, right? So one is binary search and one was the linear search we used to do, right? Even there is one more searching technique that is known as binary search tree technique. Even this is also there. Binary tree is used for searching purpose also. We can use linear search, we can use binary search, even we can use trees, binary search trees to search. These are just basic examples, basic things I am telling about the binary search trees and binary trees. Okay, now we will go to our main concept of binary search trees. What is this binary search tree? Binary search tree is most important data structure which contains a set of elements with operations like you can search, you can insert an item, you can delete an item, anything you can do on trees, right? For example, now as I told, for example, here this is a tree, I have to search for element 3. I can search or even I can insert a new element or I can delete this element. So these are the certain operations we can do on binary search tree. Okay. Now, what is this optimal binary search tree? What is this optimal binary search tree? That is, the name itself indicates binary search tree. You are using a binary search tree, okay, and we are constructing a set of binary search trees and we are seeing which tree is best for me. If I, for example, I take certain number of elements like A, B, C, D. Okay, I can take set of some certain number of elements will be given. They'll ask you to construct a tree. Okay, I'll construct some set of elements. I'll construct A, B, C, and D, or I'll construct A, B, C, D. Like this, different types of searching elements. I can add the tree and I can construct a tree like this. Many number of possibilities are there to construct a binary tree or any binary search tree taking some elements. Okay, but which one? Which is the optimal binary search tree for me? Look here, whether this is optimal or this is optimal. What is that optimality in a binary search tree? Very important thing, when you construct a tree from parent till leaves, you have to travel. For example, this is a root node, this is the parent, and these are the leaves. I need to travel from root to this nodes. Okay, what is the level I can travel? I can take this node as once. I am reaching here 1, and then from here I am coming to this node, and this is the second time I'm coming. That is, in the second level I'm coming to this, and again I'm going to this one in the second level. Okay, for example, I take some value, I take some frequencies or some value for this root. This will be multiplied with the frequencies like this. Okay, for example, you take this will be the first I can come here second, and even this one will be second, and this one will be third. Like that I can do, right? Like that I can add a new elements into an array based on this. These are the very important thing. Based on the levels I can find out the which one is optimal. Okay, that is what we have to do this in the we have to do in binary search tree. Okay, when we have this binary search tree, we have to construct many number of trees. We have many number of options to construct a tree, but which one is optimal for me? Okay, that to find out the optimal binary search tree, this technique was given, that is dynamic method, dynamic technique was given to solve such problems. For example, now why we require that technique? Why do we require? For example, look here. There is an example over here. A, B, C, and D. Okay, to be searched with the parameters. This is 1, 2, 3. These are the parameters. They'll give you certain parameters. Okay, these are the, for example, these are the 4 important nodes. I need to construct a binary tree from this. Okay, how many possibilities you have to construct a binary tree? There is one formula that is very, very important. You people have to note down that formula for construction. For example, they'll give you some set of nodes and you need to construct a binary tree from that. Okay, so when you have n number of elements, you can construct a binary tree. You have formula 2ncn divided by n plus 1. This is the formula to construct n number of binary trees. For example, look here, this is 2ncn. You have ncr. The same thing here. ncn is nothing but ncr. What is the formula of ncr? Anyone? N factorial divided by n minus 1 into r factorial. This is formula we have to apply over here. For example, I have n is equals to 3. What will be the formula? 2 into 3c 3 divided by 3 plus 1. That is 6c3 divided by 4. You have to find out the answer for this. So that is 6 factorial divided by 6. That is 6c3 divided by, this is n factorial divided by n minus 1 factorial. What is this? What will be the answer? Find out. 6c3 ಎಷ್ಟು ಬರುತ್ತೆ? Tell me the answer. 6c3 divided by 4. 6 factorial divided by 6 minus 1 into 3 factorial. What you'll get? What you'll get?
Ma'am, it will be 6 minus 1 factorial.
Wow, factorial. Okay, how much you'll get answer for this? So 6 into 5 into 4 into 3 into 2 into 1 divided by, this is 5. 5 factorial. So here this will go. And what is this 3 factorial? 3 into 2. 3 2s are 6. Right? Whatever I am doing is correct or not?
Yes.
For n equals to 3, 6c 3 divided by n plus 1 4. So this is what? 6 and 6 1. What is r? N, oh, this is n minus r, right? N factorial divided by n minus r into r factorial, right?
Yes.
N minus 1, n minus r. So this is somewhere this, that is what, that is what it will be.
5.
6 factorial divided by 3 factorial into 3 factorial, right? Divided by 4. R, n minus r factorial. That is 6 minus 3 into 3 factorial. So you'll get 6 into 5 into 4 into 3 into 2 into 1. So this 3 and this factorial will go. And there is one more 3 into 2, 6. So 6 will go, 5 4s are 20. 20 divided by 4 is equals to 5. Okay. So when you have 3 number of nodes, you have 5 different possibilities of spanning. That is 5 different possibilities of a tree. For example, I'll take one example and I'll show you. Look here, I have 3 routes, that is 10, 20 and 30. These are the 3 different number of nodes I have. I can construct how many number of possible trees I can construct? I can construct 5 different binary search trees based on this formula. Now see how can I construct? I can take 10, I can take 20 and I can take 30. This is one tree, right? Now I can take 10 over here and I will take which is greater than this, and even what I do, sorry, I'll show and I'll show. Okay, I'll take 10. Okay, instead of 20 I will take 30. Okay, I'll take 30 over here, and even I can take 20 which will be lesser. Now again I can take 20. For example, I'll take 20 as a root. 20, you can write 10 here, you can write 30 here. Okay, then now if I take one more 30 as a root, what I can do, I can come here 10 and I can come here because 20 is larger than this. Then for example, I can take 30, I can write 20, I can write 10. Look here, these are the different possibilities of a binary search tree if n number of values are given, right? Okay, that is what they're mentioning here. Look here, when you have a number of given, for example, there are 4 different nodes, you can construct 14 different possible binary search trees using that formula. That is, using that formula, you can construct 4. Without using that formula also, there are possibilities that like combinations and permutations you use, you'll get 14 different binary search trees. Okay, among these 14 different binary search trees, how can you tell that which one is optimal for you? Okay, to find out that, for example, now look here, BST is constructed using 10, 20 and 30. I have constructed like this. I have constructed 5 different number of nodes. Okay, 5 different trees. This is first tree, this is second tree, this one is third, this is fourth, and this is 5. Okay, now I need to find out the optimality of this tree. Which tree is good for me to select? Which way I can select a 10, 20 and 30, make a tree which is very optimal for me. That is, the result of that tree should be very good for me. I have to select one from this, right? So that is known as optimal binary search tree. You have to select one among those. To do that, you have certain techniques to select which tree is good for you. That technique we will be following, that is known as optimal binary search trees. Okay, constructing a tree, you have many number of possibilities. Among those possibilities, you have to see which one is best for you. Okay, so to do that, which one is best for me, for example, I'll take this node. Look here, I have constructed 5 different binary search trees. After construction of a binary search trees, look here, this is how I will represent a key with this. I can find out the frequencies. For example, each and every node, whatever you have, they will give you certain frequencies. That is, frequencies will be like the cost, or it will be like a cost for particular node. Cost or frequencies will be given. Based on that, you can calculate which tree is best for you. For example, look here, 10, 20, 30 are given. Now, how can I go this? I have to number this. Okay, so 10 is beginning. Okay, when you take this as a 10, 10, look here, this was the first element I took, and this will be the numbering will be 1 for this, and next I took 20, numbering will be 2 for this, next I took 30, the numbering will be 3. That is how you are selecting the numbers and how you are putting those numbers into the which level you are putting. That is very important. Now, based on this levels, whichever you are using, the frequencies will be given. For example, you take 1, look here, for 10 they have given 3, for 22, and for 36. So you have to multiply those frequencies with this. Then we will find out the total number of count. Okay, but first we will see how what will be the count of this, then we will go to the frequencies. Now look here, the second tree, 10 is traveled first in the beginning, 30 is traveled 2, look here, 30 is 2, and 20 is at the third level. Okay, now in this tree I am traveling 20 beginning, and then I am adding 10 and 20 at the second stage itself, second time, that is at the second position itself I am adding them. Okay, now when you take this example, look here, in this 30 I am adding first, 20 I am adding second, 10 I am adding third. Then here 30 will be first, 10 will be second, and 20 will be third. Like this you have to write down the numbering of order. Okay, that will be based on the levels only. Okay, now we have to see, look here, C is 1, 10 is 1, 10 is 20 is 2, and 30 is C 3. Now count this, 3 plus 2 plus 1, that is 6. Here also 3 plus 2 plus 1 is 6. Then count here, 2 plus 2 plus 2 plus 1, that is 5. Here you count 5, 1 is 6. Here you count, how much is this? 6. Average of all this, which one is having the lesser cost value, that is lesser C value in this? Lesser C value goes to this. Look here, you have only 5. You have 5. But based on this level, I cannot decide this is good optimal binary search tree for me. Even this can be a good optimal tree, even this can be a good optimal tree. Based on the tree balancing, that is just based on the average of comparisons. This is first comparison, this is comparison level. where I am adding. Okay, that is what C. Based on this comparisons, I can never decide a tree is optimal for me. So to do that, they'll give you certain frequencies. Okay, you're able to follow what I'm writing? So you have to multiply those frequencies with the comparison levels. For example, 10 is having 1, 20 is having 2, and 30 is having third comparison. How I will multiply that now. For example, what is the frequency of 10? 10 is having 3, and this is having 2, and this is having 6. So what is the overall this? So when you take this, it will be 3, 2 2s are 4, 6 3s are 18. So overall count this as, overall you count, you get how much? 25. So the average total overall count here is 25 with number of frequencies. That is total cost of this tree. When you consider the frequencies, without considering frequency, you will get this. Just count, just considering the count, that is just considering the C value, you will get this one as a big, this one as the optimal. But this is not good optimal binary search tree for me. Now, how to find out the proper binary, optimal binary search tree? Take the frequencies of an algorithm. Now, look here, second one. Second one, what is the cost? 21. Third one is 20, 18, and 18. So among this, sorry, 19 and 18, among this, which one is having the minimum cost? This one is having the minimum cost, and this is optimal for me. But when you did in the previous method, this was the optimal for me, right? This was optimal, but this is nowhere required or nowhere considered without any frequency. So only for that purpose we will consider frequency, and we will see which one is optimal for us. Okay, tree 5 is having minimum search count 18. So this is optimal binary search tree. Okay, so now this is what a simple normal technique, whatever I am telling you, you have to use this formula and see how many number of trees you will get. For example, if I take 3, I will get 5 number of trees. Okay, now I did this. I took 3 different keys. I constructed 5 number of trees, and I told with the frequencies, I multiplied every frequency, and I told this one is correct for me. This one. Okay. Are you able to follow? Answer.
Yes, ma'am.
Yes, ma'am.
So when you have this type, for example, only 3 different nodes are given, such number of frequencies are given, you are constructing these many number of trees, and you can write this way is very, you see this way of finding the optimal solution is okay. Okay, for me, you tell yes, this is okay, I can do. But when you have n number of values, for example, keys, I'll give more number of keys, I'll give certain 10 number of keys and 10 frequencies. How many trees you have to construct, and how you will calculate the optimality of that, right? So constructing it manually, doing like this, it will be very difficult and time consuming. Okay, so to overcome that, this type of solving can be overcome using certain formulas in our optimal binary search tree. Okay, so this is what CN formula, whatever we had taken, this one, this is okay. So to overcome this type of time consumingness, we have certain formulas, so that this, whatever the tree constructions you have, like to construct these primary type of these number of trees, and find out the optimal solution can be overcome using this formula. Okay, this is the formulas we will use to construct a binary search tree. Okay, now what is this? Look here, when you have this, I'll erase this one and I'll show you what is this. One second. Okay, sorry, I got a message. Okay, now this, whatever you have this formula, how do we get this formula? Look here, we have a tree. For example, I'll take a root node as AK, and this will be divided into two different left and right subtree. Okay, in that I have to construct optimal tree, binary search tree, with left for how many number of values? For this is AK. Okay, from AI, for example, I'll start it from I. Okay, I'll start it from I and I'll end to J, for example. Okay, I is the beginning value and J is the ending value, and this is the root. How to do this? AI till A k minus 1 will be in one set. Okay, then optimal BST for A k plus 1, next set of nodes. Okay, k plus 1, k will be somewhere in the middle. Okay, k plus 1 till A j will be on the right hand side of the tree. This is what they are given here. Okay, based on this, so that is root contains a key, that is AK. Root is nothing but AK. Left subtree. Okay, left subtree, that is, what is this? I will take it as tree t of I to the power k minus 1. This is I to k minus 1. So this subtree will be what? T of k plus 1 to the power j. Okay, this you have to see. So these two are very important things. Just T constructing a tree from I to k minus 1, and here constructing a tree from k to j. Okay, so based on that, this formula is given. Okay, look here, are you able to follow whatever I'm writing? This is just to find out the formula we are doing, that's all. Okay, cost of I comma j is equals to minimum of I k less than j. Okay, P k into 1 plus sigma of, yes, this is yes. Okay, yes, I'll write over here so that you will not get confused. C of I comma j is equals to minimum. Why? Because we need to find out the minimum, right? Optimality is nothing but minimum. Which one is having the minimum cost among everything we have to find out. So we are using minimum I less than or equals to k less than or equals to, because from I to j we have to do this. Okay, p of k into 1, that is root node, less sigma of s is equals to I, because I need to take, look here, I have to add a tree, I have to add a root node, then left and right subtree. So the same thing, this is the root node, then I should add left subpart, and then I should have right subpart. That's all. K minus 1 ps into level of as in t I k minus 1 plus 1 plus sigma of s is equals to k plus 1 to j ps into level of as in tk plus 1 to j plus 1. This is the formula to find out the minimum among the tree. Which one is minimum? We have to use this formula. So we have to substitute. We have, that is what formula? That is, look here. This is what minimum. I have to take root into 1 plus ps, that is from this optimal tree. Ps of level of as in optimal tree from this side plus optimal tree from this side. I have to find out which one is minimum among that, and then I have to get the answer. Look here, minimum of I is less than or equals to k less than or equals to j, s equals to I to k minus 1, that is this one, left subtree, ps into level of as in this one, left subtree, plus this right subtree. This is right, this is left. So finally combine them, you will get this formula. That is C of I comma k minus 1. This one, look here, I to k minus 1 plus C of, that is cost of k plus 1 to j plus overall distance, that is overall optimal cost, that is, this will be the frequency from this to this, how much time you are taking. This is the overall frequency, optimal frequency. This is very important formula for you to find out the optimal binary search tree. Okay, look here, this is the formula. C of I comma j equals to minimum of C of I comma k minus 1 plus C of k plus 1 comma j plus the distance. From that to that, how much will be the distance? Based on this, same thing, I have to see which one is minimum. Okay, I have to apply, keep on applying based on the number of cost. Okay, but I have to do that for 2, 3, 4 costs, and I have to see which one is minimum. I have to get that. This is the formula to find out. Okay, so where C of I comma I minus 1 for 0 represents the empty tree, and I comma I equals to P for 1 less than or equals to I represent one node tree. When I this is equals to 1, it is a 1. If it is 0, it is for empty tree. So this formula is very important. Now based on this formula, we will be calculating the binary search tree. This